Hello, Djordje Romanic here. Welcome to Fundamentals of Weather and Climate playlist. Let us discuss how saturation water vapor pressure depends on temperature, which we already established conceptually in one of my previous videos. This functional dependency is extremely important in atmospheric sciences, and we spend a lot of time studying it. The dependency is an exponential function like so, where on the y-axis we have saturation water vapor pressure, and here we have temperature. Perhaps temperature is in degrees Celsius, and this saturation vapor pressure is in hectopascals. And you know by now that 1 hectopascal is equal 1 millibar, which is also often used unit in atmospheric sciences. This is the functional form that we want to study here. And this is an exponential function. Now, just to throw in some values so that you are familiar with what we are talking about here. For example, at 0 degrees Celsius, saturation vapor pressure of water vapor in our atmosphere is 6.11 hectopascals. For example, at about, let's say here, 10 degrees Celsius, saturation pressure is about 12. So clearly this is not to scale, but you get the point. And then, I don't know now other values, but you can see at 20 degrees Celsius, saturation pressure jumps a lot. So what this curve is telling us is that the relationship between saturation vapor pressure of water vapor and temperature is not linear. This is a nonlinear function, and this function has name, and it's called Clausius-Clapeyron relation. That is basically differential equation that says that the change of saturation vapor pressure of water vapor for a small increment of temperature change is equal LV divided by RV T squared. And this is called Clausius-Clapeyron equation, where ds is infinitesimal change of saturation vapor pressure, dt is infinitesimal change of temperature, LV is the latent heat of vaporization, 2,500,000 joules per kilogram, and RV is gas constant for water vapor, 461 joules per kilogram per Kelvin. Please keep in mind that here in this equation, ES is in pascals, not hectopascals, pascals, and temperature T is not in Celsius but in kelvins, if you want to use it. Given that this is fundamental playlist, I will not go further to solve this differential equation. We will do that a lot in advanced playlist. But I could say that if you want to use this equation, but you don't know differential calculus, then you can say, let's say here, that dES is approximately some finite difference, delta ES, and dt is approximately some finite difference, delta T. So, for example, delta T of 1 degree Celsius, you can calculate what is delta S in pascals. This is approximation, because mathematically equation is only analytically correct for infinitesimal differences. But this is how the saturation water vapor pressure depends on temperature, and the relationship is, as you can see, not linear but rather non-linear. As you can see, non-linear, it depends on the 1 over T square. Let us now look further into this figure and consider basically 3 regimes that we can have in this system. One regime is if the partial pressure of water vapor, let me write it here. One regime is if the partial pressure of water vapor is smaller than saturation pressure of water vapor, and that would be in this region over here. Over here, we would say that we have unsaturated atmosphere or the environment. Because if I am over here, notice, if I am over here, for example, temperature is 10 degrees Celsius and partial pressure of water vapor is 6 hectopascals, well, that is below 12 hectopascals, what is the saturation value at 10 degrees Celsius. So we are unsaturated or below saturation. Then we have case when E is equal ES, and that is exactly, of course, this curve. When we are on this curve, then we are achieving saturation. This is saturation that we discussed. And lastly, we can also be in the domain when partial pressure of water vapor is larger than the saturation. And this is very transient condition. That would be, of course, somewhere here, not somewhere. It would be this region over here. This is the so-called supersaturated environment because momentarily air has more water vapor than the saturation pressure, and we will have very intense condensation and the system will go back to equilibrium. In other words, imagine that at 10 degrees Celsius, the actual amount of water vapor in a volume of air is such that water vapor pressure, E, is perhaps 15 hectopascals. Well, this is oversaturated environment. It is not in equilibrium. So the system will tend to go back to equilibrium, and equilibrium is over here. So this is very transient condition, but nevertheless it can exist in the atmosphere, and it does exist in clouds in some cases, okay? So this is called undersaturation, saturation, supersaturation. Now I would like to discuss the difference between saturation vapor pressure over liquid water and saturation vapor pressure over ice. The reason we can discuss that to begin with is already obvious in this graph, because notice when temperature is at 0 degrees Celsius, freezing, that this value over here is not 0, but rather 6.11. That means that at 0 degrees Celsius, we do have water vapor in the atmosphere, which means we can also have water vapor in the atmosphere when the temperatures are below 0. So let us now kind of zoom in the negative part of temperatures and extend this curve for liquid water and ice. I'll do that after erasing this. In the previous slide, this relationship was explained for positive temperatures. Now we want to focus on negative temperatures. First of all, we have to know that in the atmosphere, liquid water can exist at negative temperatures. And that phenomenon is known as supercooled water, and my previous video explains it in great detail. However, we can also have ice at negative temperatures. So, in the atmosphere, at temperatures below 0, let's say negative 10 degrees Celsius, we can have liquid water and we can have ice. So, consequently, this curve will split into two curves in this region of negative temperatures. There will be continuation that explains saturation vapor pressure over liquid water, and there will be continuation of this curve that explains saturation vapor pressure over ice. And this over here is the saturation vapor pressure over ice, and this over here is the saturation vapor pressure over liquid water. And the saturation vapor pressure over liquid water, as you can see from this relationship, is larger than the saturation vapor pressure over ice. You can see it. And the difference between these two curves is very, very small. I exaggerated it here. For example, if we have temperature, let's say here is temperature of negative 15 degrees Celsius, then this saturation vapor pressure over liquid water is about 2 hectopascals, whereas the saturation vapor pressure over ice is about 1.8 hectopascals. Very small difference. But these small differences play enormous role in the thermodynamics and dynamics of clouds. Formation and development of clouds heavily depend on this relationship. And formation of precipitation is particularly dependent on this relationship, as we will discuss in great details in my chapter on precipitation. What I would like you now to understand is two things. First, that the saturation vapor pressure over liquid water is larger than the saturation vapor pressure over ice. It is described using these relationships graphically and using Clausius-Clapeyron equation that I outlined in the previous slide. It is also important to note that the difference is very small between these saturation pressures, but nevertheless very important. And the third and the last thing is what many of you probably are now saying. And that is, why are these different? Why is it that the saturation pressure over ice is actually smaller than saturation pressure over liquid? Why is it not the other way around? Or why is it that they are not exactly the same? And the answer to that question is easily provided if you watched my video on why is water so special. In that video, I explained the origin of hydrogen bond. And you know that water molecules in both liquid and ice are held together by intermolecular force called hydrogen bond. Now, in ice, the thermal jiggling is so small that the hydrogen bonds dominate the structure, and the ice forms this crystalline structure where all water molecules form this hexagonal shape that I explained in that video. Now, in liquid water, we still have attraction between water molecules through hydrogen bond, but that attraction is also counterbalanced by thermal jiggling. So water is liquid, it's all over the place. How is that related to this? Well, in the following way. What is saturation vapor pressure? From my previous video on what is saturation vapor pressure, you know that saturation vapor pressure is the equilibrium state. That means, on average, for every molecule that evaporates from liquid water, for example, there is another molecule that condenses. So there is no net condensation or evaporation. And the same is for ice. For every molecule that sublimates from ice, there is another molecule on average that deposits on ice. And now is the key. And the key is to put all this together. You see, it is much more difficult to extract water molecule from ice, because ice is that crystalline structure. Hydrogen bonds are very strong. There is no thermal jiggling of great extent to disrupt them. So to extract molecule from ice is much more difficult. And that means there is less water vapor molecules above ice because it's more difficult for them to escape. And that means that there is less need for molecules to go from vapor to ice to establish equilibrium. Whereas in the liquid case, it is easier for liquid water molecule to escape water because they are already jiggling very much, and hydrogen bonds are affected by thermal jiggling, and therefore there is much more molecules that need to condense to keep that equilibrium. Well, much more molecule above liquid water means that saturation pressure over liquid water is high. Small number of molecules, water vapor molecules, above ice that is required to keep equilibrium with sublimation from ice means that the saturation vapor pressure over ice needs to be smaller, and consequently, indeed, saturation vapor pressure over ice is smaller than saturation vapor pressure over liquid because, in one simple sentence, as I said, it is more difficult to extract molecule from ice than it is from liquid water. And that explanation that I provided results in these two curves being different and ESI being below ESL. And this difference plays enormous role, as I said, in cloud physics. We will see, I will just say it in one sentence, that in cloud, if we have ice here and liquid water here, where are water vapor molecules more likely to go, to migrate? They are more likely to migrate towards ice because water vapor pressure over ice is lower. So if we have water vapor and we have one ice particle and we have one liquid water particle at negative temperatures, the water vapor molecules are more likely to migrate towards ice, and ice will therefore grow at the expense of water vapor in the atmosphere. Eventually, this liquid water will also evaporate, and that evaporated water vapor will serve to grow this solid ice. I will discuss this in much more details later when I talk about the so-called Bergeron process and precipitation formation. But I hope this is clear conceptually, together with the previous part of the lecture where I established this nonlinear curve known as Clausius-Clapeyron equation. Please make sure to like and subscribe, share this video with your friends and enemies and family, girlfriend, boyfriend, and until next video, goodbye.